Okay, take it away.
All right. Yeah, thank you so much. And thank you for giving me the opportunity to give this talk. Um, what I'm going to talk about is twisted K-theory via homotopical algebra, and that is based on a survey that I wrote together with Ulrich Bunke and Markus Land, who are both in the audience. So let me start by giving you a little bit maybe of motivation. So, as probably all of you know, if you have a compact, smooth, and orientable manifold with our boundary, and the dimension is n, then this thing has a fundamental class, right, which lives in the homology in degree m with integer coefficients. So this is the fundamental class. And now if you drop this orientability condition, so if you scrap this, then you don't have that anymore, but you still have a replacement, a fundamental class that lives in the nth degree homology with local coefficients. So this is homology with local coefficients. And this thing here is the local coefficient system. Right, and if you want to be really precise, then what this is you take the orientable double cover, which you can see as a Z mod 2 bundle over your manifold M, and then you just associate to that the integers with the plus, with the sign action, and that maps down to M. This gives you the bundle of local coefficients. Right, and something very similar happens in K-theory, right? So if I have M spin C manifold with all of the other adjectives that I'm not going to write down again, then there's a K homology fundamental class given by the Dirac operator, by the class of the Dirac operator on this manifold. And we've seen this in the very first talk that, so this is an elliptic differential operator on your manifold. And as such, it gives rise to a class in KK theory. And this plays the role of the fundamental class in K theory. And this is very much like an orientability condition, but for K theory. This is sometimes also called K orientable. So again, you can ask what happens if I don't have that, if my manifold is not spin C. So if I drop K orientability, then, well, I don't have this Dirac operator anymore, but I still have a Dirac operator that works, that acts on the Clifford algebra of M. So I get a class in the K homology of the section algebra of the Clifford bundle over M. And okay, so I should maybe, so this is the K homology of this algebra. This is the K homology of this space. I'm sorry about the indexing. That's just history. So this plays the role of, so this is like K homology with local coefficients, if you like. So if you see this, then you could, in general, start to study K theory and K homology of oops, bundles of C-star algebras of this type. I'm sorry. This will happen a lot. And this leads to the definition of twisted K-theory. Can I switch this off? I can't. As follows. So if I have a bundle of C-star algebras, over, let's say, a compact Hausdorff space X, I can define the twisted K-theory in the following way. So this is now twisted K-theory of the space X with the twist given by this bundle of C-star algebras. I can define this as the operator algebraic K-theory of the section algebra of this bundle. And by bundle here, I really mean bundle in the topological sense, i.e. a locally trivial bundle of C-star algebras. So where the structure group is the group of star automorphisms of a C-star algebra equipped with a point norm topology. So there's a good notion of locally trivial bundle of C-star algebras. That's the one that I mean here. And a little side remark is, so note that if I do this, then this twisted K-theory is a module over untwisted K-theory. Oh, I'm seeing that there's some activity in the chat. I don't see the chat at the moment, so if there are any questions, please let me know. All right, so a little bit about the history of this. So this was first studied by Donovan and Karoubi in 1970, where they looked at bundles where the fibers are, so these essentially bundles of matrix algebras. And they, for example, found out that if I do this, then up to non-canonical isomorphism, this twisted K theory that I get from this only depends on the class of this bundle in the so-called Brouwer group, in the unitary Brouwer group, U of X. And this is isomorphic to the torsion component of H3 of the underlying space. So you can sort of classify up to isomorphisms all of the twists that they considered. They did a bit more. They did this also in the real case and also with grading. So there's a lot more that they have in this paper, but that is maybe the part that's most relevant for this. Okay, then later Rosenberg in 88 and Attia and Siegel in 05, they looked at bundles of compact operators. Or in the case of Attia and Siegel, or bundles of projective Hilbert spaces. Projective Hilbert space bundles. And you can also classify these. And so the classification here is a locally trivial bundle of compact operators are classified by this. And that turns out to be isomorphic to the third cohomology of X with integer coefficients by the so-called Dix-Medullari class. All right, and so I gave you this motivation using orientations, orientability. There are other motivations as well. For example, there's a very interesting theorem that involves twisted K theory by Fried, Hopkins, and Telemann, which in its simplest case says the following: if I have a compact, simple, and simply connected Lie group and a number or a class M in the third cohomology of the group, which with all of these adjectives just turns out to be the integers, then I can look at two things. I can look at twisted K theory in degree given by the dimension of the group with a twist depending on this integer, which I will just denote by, I don't know, curly km. And then equivariantly of the group as a topological space where the group acts on itself by conjugation. So that's one side. And the other side is the so-called Velinde ring. Oops, that should be an M. So there's a representation theory which you can do for the associated loop group, which is sort of a projective representation theory, and it depends on the level. That's this M here. And then you have this isomorphism here. This is something that comes up a lot if you do conformal field theory in 2 dimensions. So this is interesting in mathematical physics. And this is kind of the computable side. This is something that you can, because it's coming from topology, you can actually compute this. So this is another motivation why you should consider this. And you can write this thing down actually as one of those bundles here. You can express this in terms of bundles of compact operators. So it is one of those twists that people have considered before. Okay. So that's kind of the a little bit about the C star algebraic side of things. Of course, I mean, if you want to do homotopy theory, then maybe you should do something completely different, right? So here's the homotopical picture. Homotopic picture. So what we want to do is we want to reformulate this definition of twisted K theory, right? By the idea of, I mean, using what we know, right? So what we've seen yesterday is that we have this functor K theory, which takes you from C star algebras into the category of spectra. And the right notion that you should maybe consider here are the KU module spectra, right? So this is the homotopical way of seeing K theory. And so I could look at this, of course, right? So I have my bundle of C star algebras. And instead of taking the operator algebraic K theory, I just take the spectrum valued K theory functor. But that's kind of the wrong idea, because really what you want to do is, instead of this, if you have this bundle of C star algebras, you want to take this spectrum valued K theory functor fiberwise. To get a, let me put this into quotes, to get a bundle of spectra. And in this case, KU module spectra. And then you want to take global sections. So the question is, how do you make this precise, right? Because you have to be very careful with this. This has been done, like people have worked with this a few times in the literature. So there's a paper by Ando, Bloomberg, and Gebner where they developed this in the context of infinity categories in a slightly different way that I'm going to present it. And then there's a paper where they work with explicit models by Hebestreit and Zagave, who also uh, look at this. And instead of bundles, you see I put this in quotation marks. So really what is better in terms of better behaved in terms of homotopy theory are not bundles in the locally trivial sense, but so-called local systems. So here's the definition of what I mean by a local system. So let's say I have an infinity category C, and X is an object in C. Then I can look at B out C of X, which is the full subcategory of the groupoid core of C on objects that are equivalent to X. Right? And then I have a category of local systems. Let's say on a space W with fiber X. And that category is just the category of functors from W now considered as an infinity groupoid into this category B out C of X. Right, so that's a local system. And if you think about it, this is kind of the correct homotopy theoretical generalization of a bundle, right? So what does this do? If I pick a functor in here, what it would do, it would associate to each point, it would associate an object that is equivalent to this X here, to each like path between 2 points. It would associate a morphism between an isomorphism between these two equivalent objects, and so on and so forth, and all higher coherency data. So that makes sense, right? Okay, so that's kind of the right homotopy theoretical generalization of what we will mean by bundle. And then I still need another ingredient. So I have a localization functor L. We've seen that yesterday as well, from topological spaces to spaces or anima. And that's just the localization at the weak equivalences. And one can kind of make the image of the topological space X under L a little bit more precise by using the following convenient description. So I have the simplex category of X, which has as its objects all of the simplices in X, and as the morphisms, I have maps in the simplex category delta, such that this diagram commutes. Right, and that's one category, right? And then I can write the image of L as the co-limit on the constant functor that just associates everything the point over this simplex category. And then it turns out that the canonical functor from the simplex category to L of X is also just a Dwyer-Kahn localization. Is the localization at all morphisms in simplex category.
There's a question in the chat, namely what happens if W is the Cantor set? So should we pose any conditions on W, I guess?
You mean
I think probably this should be the space the bundle is over, but maybe the
I mean, this always works. It just remembers the weak homotopy type of the topological space. So far, I don't make any restrictions. The statement that will come in a few moments will depend on a regularity condition. So that's where I've put this. So at the end of the day, we can only say something about spaces that are homotopically finitely dominated. So which is like the regularity condition that we will use.
Thanks.
Help? I don't know. Right. Okay. So I have this description, and now here's the crucial observation is that now I have a way of creating a bundle of spectra in this local systems way from my bundle of C-star algebras. So given this bundle of C-star algebras with typical fiber A, with just write fiber A, gives rise to local system. And this works as follows, right? So I, from this bundle, I can construct a pre-sheaf on this simplex category. With values in C-star. Okay. And that works, well, that's not difficult. You just associate to a simplex in X the section algebra of the pulled back bundle, right? So like this. And then this extends to functors. You can easily check by mapping this to the corresponding restriction maps. And then, I mean, we like simplices for a reason, right? So we note that this bundle here is a contractible space, right? So this bundle is trivializable. The pullback is trivializable. So this is actually the continuous functions on the simplex with values in the typical fiber. And it's also then homotopy equivalent to just A, right? Because the simplex is contracted. And here I'm now using that this is so that A is locally trivial. All right, so what do we have? Now I have the pre-sheaf on the simplex category with values in C star algebras. I can go from here to this localization at homotopies, and then I can go from here to L of X op. And because I'm sending all of the maps here now to equivalences, this will factor and give me a map here. And this is an infinity groupoid, so this is equivalent, it's equivalent to L of X. And you can check that actually, since you're mapping always to something that's homotopy equivalent to the typical fiber, you factor over B out in C star H of the typical fiber. So, and this is the associated local system now. And now I can make sense of my bundle of spectra. So I can just compose this with the K-theory functor, and then I get a map from Lx to B out C star H of A. Composing with K-theory brings me to B out in mod Ku of K of A. Right, where this is this local system that I've constructed before, and here I'm applying K-theory. And now I can define the global sections. So this is gamma of X. Oh yeah, maybe I should give this a name. So this thing, this composition here is K of A. So now I can define the global sections using the limit. In module spectra, or the K-theory spectrum. Right, okay, so that's the homotopical picture of twisted K-theory. And now the proposition is, and this is also in the survey, that if X is homotopically finitely dominated, then actually the two constructions are equivalent, right? So the K-theory spectrum of this section C star algebra is actually equivalent to the sections of this bundle of K-theory spectra.
We have another question, namely, does this, I guess the global sections you write above object vector through sheaves on C-star algebras?
Yeah, sheaves are not really
Yeah.
good in this context because sheaves are usually based on having like on things associated to open sets, right? And that causes problems here because I mean here you really want this to be this. This works because these are nice compact spaces here, right? If I have C0 of an open set with values in A and take the K theory of that, that's not just given. It's not like that. That's I have to. Yeah, this is like relative K theory to the one-point compactification again, right? So that's why sheaves don't really work here, and we had to go through this alternative route using simplices.
Thanks.
Yep. I wanted to say maybe a few words about the proof of this. By just telling you like what the map is that you get from like left to right. So what we actually have to do is we compare the two functors from compact Hausdorff spaces over X to mod KU, where the first one is sending a space over X to this, and you can guess what the second one does. It will go from to, and yeah, so of course, I mean yeah, I've written the L here. Okay, that's fine, right? I mean, this is Y considered as or identified with its underlying infinity. Okay, so we have a natural transformation on of functors on the simplex category where one is the constant functor and the other one is this pre-sheaf that I've constructed here for the pullback. Is phi, but for f star. And that's just given by restriction, right? So, or by pullback with this map from the simplex. So just as before. And then combining this, composing this with K, gives a natural transformation, or gives natural transformation this to this, and then using the fact that we have defined the right-hand side here as the limit, we get a map rho f from here to gamma y k star a. And then one has to work a bit to see that this thing here provides a natural transformation. And I don't want to go into that. But what one then can do is one can then use this tameness assumption on X here and reduce everything to the case where X itself is a CW complex and run an argument by induction over cells. So then reduce to case X is CW complex and use cell position. So that's at least, I don't know, the ingredients of the proof. Right. And I want to spend the second half to outline. I mean, so this gives you like an identification of these two pictures of twisted K theory, where this is the more operator algebraic side, and this is the homotopy theoretic one. And now one can take the homotopy theoretic picture and ask questions like, well, what kind of twists do I have? Can I classify them in some way? And then go back to the operator algebraic side and ask, can I find a C-star algebra, a bundle of C-star algebras that somehow realizes these twists? And so there is a connection between the two pictures of twisted K theory and a class of C-star algebras from classification program, and these are called strongly self-absorbing C-star algebras. And I wanted to outline how these two things fit together. So first there's an observation. So if we look at KU, so topological K theory, or I mean, this is K of C if you like. So this is a ring spectrum. It's a commutative ring spectrum. So there's a space of units that this has, which is usually denoted by GL1 of KU, and it's defined using a pullback diagram. And it turns out that in the case of K theory, this is actually a commutative group GL1 of U in spaces. So like, okay, so a commutative group in spaces is just a, well, it's just a connective spectrum. So there's a connective spectrum where this is its underlying infinite loop space. And then that has an associated cohomology theory. And it turns out that the first group of this cohomology theory, so if you like the maps from X to BGL1 of KU, that's the group that actually classifies the all possible twists of K theory. And so keep this in mind. So then I want to introduce another thing. If I have symmetric monoidal infinity category, then a morphism in this category, epsilon, from the unit object to some other object x, is an idempotent in C if the morphism epsilon tensor it from x, which is equivalent to 1 tensor x, which then goes to x tensor x, that if this is an equivalence. And it turns out that in the category of, in this localization of the category of C-star algebras at homotopy equivalences, there are idempotent objects, and these have been discussed by the operator algebra people a lot. So here's the definition: unital C star algebra A is called strongly self-absorbing if I can find an isomorphism phi from A to A tensor A, where this is the minimal tensor product, and a path U from the half open interval to the unitary group of A tensor A, such that if I let this path go to 0, then it asymptotically conjugates this isomorphism onto the right tensor embedding. It doesn't matter whether you pick the left tensor embedding or the right tensor embedding, but it's a big one. And so how on earth is this an idempotent object? Well, so the remark is this thing here, star, gives a path between the right tensor embedding. And an isomorphism. Right? And if you look back at the definition of what an idempotent in C star H is, it's exactly, well, it's not exactly that, but this condition here will imply this, right? Because then I have a C star algebra A here, and I have this path that connects the right tensor embedding, like this one, with an isomorphism. And now you might, well, I mean, this looks really strange if you see this for the first time, and you might wonder, I mean, you start with a C star algebra that is isomorphic to the tensor product with itself. So uh, are there even such things at all? And there are some examples. Well, the complex numbers is the trivial example, but then there are the so-called Kunz algebras, and two of them, O2 and O infinity, have this property. And then maybe more concretely, I can take the n by n matrices on the complex numbers and just take the infinite tensor product. So I take the co-limit over all of these matrix algebras. That's also of this type, so it's also strongly self-absorbing. And then there's the so-called Jiangsu algebra, which is also strongly self-absorbing. I can form tensor products of strongly self-absorbing C star algebras, and these will be strongly self-absorbing. And just as an explanation, so that this is not just a letter, what is this? This is the universal C star algebra generated by countably many partial isometries Si. So these satisfy property that Si star Sj is equal to delta Ij times the identity. And delta Ij is just the Kronecker delta.
So we have another question, namely,
Yeah.
an idempotent has an additional structure, namely a multiplication. So is there also an additional structure in this C star setting?
Um, yes, there is something that I want. I mean, that's the next point. Is that yeah? I mean, yeah. So this you can think of, or you can think of the inverse as giving you some kind of multiplication here. And of course, I mean, now if I have this in C star alg H, then it will carry through to everything that is symmetric monoidal, right? So for example, on K theory, um, I get the following statement. If this, and by this map, now, yeah, right, I should have said this. So what's the map here, right? So this map here from the unit to here, the unit in C star algebra is, of course, the complex numbers. So I need a map from the complex numbers to the algebra. That's, of course, the unit map. I'm assuming that my algebra has a unit, right? So that's the map that I have. That's the thing that I want to be an idempotent. So if this is an idempotent in C star H, then, so first of all, this has a canonical structure it's a canonical structure of commutative algebra in KU modules. Right. And so that's um, something that you wouldn't expect, right? In general, if I take the operator algebraic K theory of a C-star algebra, the best thing that you get is usually you could just get an abelian group. But here, because you start with one of those idempotents, you get an additional ring structure on K theory, and you see this on the level of spectra here using this. Okay, the other observation is whenever you have an idempotent, you can think of the functor of tensoring with A um, LA given by blank tensor A. This is a localization functor. Again, this is just from the abstract theory of idempotents. And in particular, I can take the localization of C star H at A. The unit object in this is A, and the tensor product carries over. So this is a symmetric infinity category.
I have a question on the lemma. Is
Yeah.
being a commutative algebra in KU modules any more structure than being a commutative algebra in spectra or more properties?
I mean, it is compatible with the with the KU module structure as well, right? So that's the
Right. So like, does that give you anything like concrete that like is practically useful?
oof, I'm not sure. I think this might just be the statement that is compatible with bot periodicity or something.
Okay, no worries. Thanks.
Yeah. Right. So I get this localization. I also can look at the mapping space. And this has now this has two structures now, right? So I can compose these endomorphisms. That's one structure, and a priori this is just associative, right? There's nothing else to expect. But it also, because it kind of lives in here, it also has a tensor product structure. And because I started with, and the tensor product is of course commutative, so I have the composition. I have the tensor product structure, which is the commutative structure. So, and then these two fit together, right? So I have like a commutative monoid in monoids, if you like, and there's like an Ekman-Hilton type argument that tells you that actually these two structures are equivalent. So in particular, we get and here um, I can take the anima associated to the endomorphisms of the C star algebra A tensor the compact operators. This even though it's not unital anymore, it's also, I mean, for that reason, it's also not strongly self-absorbing, but it is still an idempotent in C star alg H. So I can look at this. This is equivalent to the mapping space in C star alg H of A tensor K, A tensor K. Then I can apply KK and end up in the infinite loop space underlying KK A. Now I can drop the compact operators because KK theory is stable. And then I can pull this back using the unit map of A and end up in omega infinity K of A, right? Where I pull this back with the unit here. And then I get this map that restricts to homomorphism of commutative groups in spaces from here into GL1 of KA. Right, and one thing that you can now ask is, well, is there anything that will give me K of C here? Well, if I put in C here, then I get KU. However, if I put in a C here, if I replace the A by the complex numbers, this is too small, right? We know the automorphisms of the compact operators. For the compact operators, this will not be an equivalence. But there is a C star algebra that makes this an equivalence. And maybe that's also the last thing that I want to mention. So for A equal to O infinity, this map is actually an equivalence. And it turns out that, so the K theory of O infinity has the same K theory as the complex numbers. So this turns out to be GL1 of KU. And we could, like, for all of these strongly self-absorbing C star algebras, you can determine like what the right-hand side is in terms of GL1 of KU in some way, shape or form. But maybe this is a good place to stop.
I'll thank our speaker.
Thank you.
Are there any questions? Okay, so I will turn off the recording.